Welcome. In this episode, we're going to talk about simple harmonic motion. It's a new topic. And so we're going to start off by defining what simple harmonic motion is because it's not a very easy term to understand. It's hard to break down what it means. So simple harmonic motion is just a vibration of an object about an equilibrium position that is caused by a restoring force that is proportional to the object's displacement. This is kind of a long definition. But all it is we see it in pendulums, and that's why we've been doing pendulum labs. And we also see it in springs, and that's why we've done spring labs. Any object that vibrates about a position where it normally wants to rest undergoes a simple harmonic motion. There are some key terms that we need to look at, though, such as it is caused by a restoring force that is proportional to the object's displacement. All right, so we need to have this proportionality of the force and the object's displacement. And we see that in the springs, and we've even done a lab where we've looked at that and actually came up with an equation or somewhat of an equation to figure out that those two things were proportional, that the displacement of the spring and the force on the spring or force caused by the spring was proportional. One thing that we haven't tested was the pendulum to see if the force was displacement or the force was proportional to displacement. But it works out, in fact, as long as the spring or the pendulum's angle is small, such as 15 degrees or less. So it's hard to pick that up in a lab. And so what we're going to do today is we're going to talk about uh, this simple harmonic motion, and I'm going to give you some equations to help us predict and calculate various aspects of it. The first thing I want to do is I want to go ahead and talk about some vocabulary that I'll be using today. And you've probably seen these before, but let's go ahead and review, and then I'll show you more specific examples when we get to the pendulum and the spring. The first vocabulary word is going to be amplitude. Now, the amplitude is just the maximum displacement of the object from its equilibrium. And it just so happens that when the object's velocity is zero, so think of it as whenever the pendulum's all the way at the top of the swing, its velocity is zero, then it's at its maximum amplitude. So that's its amplitude. All right, and it's measured from the equilibrium point. And once again, I'll point this out to you whenever we discuss each individual time or situation. It is measured in meters, and which we'll also talk about later. The next one is the period. Now, the period is the time it takes for the object to complete one cycle, and we've already did this in the pendulum lab that we just completed, and so we should have a good understanding of what the period is. On the pendulum, it's the amount of time it takes to go from one side down through the bottom all the way up to the other side and stop, and then come all the way back. On a spring, it's the amount of time it takes for it to bounce back up, stop, and then come all the way back down to its lowest position. And we measure that in seconds. Now, this is a new word that we haven't seen yet, and it is the frequency. The frequency is the number of cycles in 1 second, and it's going to be measured in hertz or per second. All right, and as you can see, these two are inverses of each other. We have seconds, and we have per seconds. And so this is going to be our first equation that we're going to use. And it's going to be that the frequency, which is an f, a lowercase f, equals 1 over the time period. Right? And this goes back and forth. So the time period is going to equal 1 over, hold on, 1 over the frequency. Now, if you're a runner, this actually helps out on quite a bit of things. Whenever I run, I have, there's two ways of determining your speed. You could go miles per minute, or you can go minutes per mile, which is your pace. All right, so this miles per minute is your speed, the minutes per mile is your pace. Same thing down here. Now, this is a per second, so we need to think about it. It's going to be cycles per second, and this is the number of seconds it takes to go one cycle, just to clarify. All right, so let's go ahead and move on to the more specific situations. And so here I have a spring, and we did a lab where we were supposed to kind of figure out, well, what was going on with the spring and what was the restoring force on it. And that restoring force, so let's go ahead and write this down here, restoring force, the restoring force on a spring follows what's called Hooke's law. All right? And that is the restoring force. So F restore is what we'll call it. The restoring force on a spring is equal to negative kx. Now x is the displacement and k is the spring constant, and that's specific for each individual spring. Now this negative sign here just shows us that it's going in the opposite direction of the displacement. All right, so on this spring over here, this is its equilibrium point, is this dashed line all the way down the center. And so if I were to look at this, here the spring is not stretched or compressed, but then I go ahead and compress the spring in that direction. All right, and so the displacement is to the left, and so we'll call that negative, but the spring wants to push to the right, and so that's going to be a positive force, and so the two negatives cancel out. Now, whenever I do this, let's say I pull my spring back and then I let it go, well, it's going to push the mass or push the spring forward, but it's not going to stop at the equilibrium point because it has some energy in it, which means that it's going to continue to move, and it continues to move to a point that is equal away, just like on the pendulum, how it swung up to equal angles. So it's going to push to a point that's equal away, and it's going to have a restorative force that now, so let's go ahead and mark the restorative force here on this one. So the restorative force is in blue, all right, and it's going to point back the way that opposite the compression. And then in this case down here, the displacement is in that direction, and the restorative force will point back in that direction. All right, and that's where that negative sign comes in. So we can calculate the restoring force by if we know the spring constant and we know how far it is compressed or stretched. So the red is delta x, or just x, and the blue is F. Okay, so that's the restoring force on a spring. Now, on a spring, you have to imagine that this spring, whenever I compress it, it's going to just wobble back and forth across this equilibrium position. And if you notice, if I were to connect all these, it's going to make somewhat of a wave. And we'll talk about waves later, probably in the next video. But right now, we just want to talk about the other parts of the spring, such as how can we calculate the period of a spring, the time period. The time period of a spring comes from the equation where we can calculate it using 2 pi equals the square root of m over k. So when we talk about the time period of a spring, it's going to be given by this equation right here. Now, we haven't really seen this square root symbol in an equation before, but it's really simple to get rid of it. All I have to do is whenever I get this 2 pi over to the other side, if I want to solve for m or k, then I just square both sides. And so that, and I'll show you how to do that on an example problem. But right now, this is the base problem for what we're looking at, the base equation. Okay, and so that would be springs. Now let's talk about the next situation. Oh, I want to come back to this real quick. I want to talk about velocity of the object and the acceleration of the object. Okay, at this point, at the top, right here, when I'm at equilibrium, the spring is not stretched or compressed, and so that means that it has a force or restoring force equal to 0. So if the force is equal to 0 at the equilibrium position, then that means acceleration has to be equal to 0 also at those locations. But what does that mean after I let go? Well, that means the force is greatest at its compressed position and also equally stretched. So here the force is going to be the max, which means acceleration is going to be max. All right? But the amplitude says that this should be a 0 velocity, and that's the case because I pull it back and it stops, and then I let it go forward, and it's going here, and then it stops right here, but right before it gets pulled back. So velocity equals 0 at these points. Another thing that I notice is if the velocity is 0 here and acceleration is 0, that means it accelerates through this length or through this displacement. But then at this point, there is no force on it, which means that it has to be going the fastest. Because once it gets past that point, well, then the restoring force is in the opposite direction, and it slows the object down. So when it's at equilibrium, velocity equals its max. Okay, I think that's it. If not, I'll have to come back to it. So now let's go talk about pendulums. Now pendulums, here I have a pendulum, and if you see the pendulum, I pulled it back to this location, and I let it go, and then it's right here is its equilibrium position, and then it swings back up, and then it goes back to the equilibrium position, and it swings back up. Now in this case, the restoring force of the pendulum is gravity. Gravity pulls the pendulum down. So when it's up here, it has a force of gravity that points straight down. All right, and its restoring force, which we'll put back in blue, is a component of that gravity. And it's going to be somewhat like that right there. And then at this next position, so once it goes back to its equilibrium, the restoring force is going to be straight down. But there is no, or the force of gravity is going to be straight down, but there's no restoring force because there's no component of the gravity in the direction of motion. If I look at the next one, gravity points straight down. And the restoring force is in that direction right there. And once again, gravity points straight down. There is no restoring force because there's no component of gravity in the direction of motion. In this case, the restoring force is going to be down in that direction again, and the force of gravity is going to be down. Just like that. So, once again, to go back to velocity and acceleration, I know that up here my velocity is going to equal 0 at my maximum height or my maximum amplitude, and acceleration is going to be my max. Okay, here velocity equals max and acceleration equals 0, and then likewise as I go down. Once again, if I were to connect these positions, I would have somewhat of a sine wave or a cosine wave. So the restoring force is gravity, and it's not simple to calculate. There's no, we have to look at force diagrams, and we have to break the force of gravity down to its components. And then because the force of gravity changes as the pendulum swings, that brings up another level of complication to this. Once again, the restoring force for a pendulum only works if the angle is about less than 15 degrees. Now, the time period for a pendulum, though, and this is what we did our lab on, and we should have all seen it, and I think we did for the most part, is that the time period for the pendulum, or the amount of time it takes the pendulum to swing back and forth, is not related to the object's mass. So the object's weight has nothing to do with it, or the object's mass has nothing to do with it. Another thing that we also noticed was that no matter how high you pulled it back, the period was the same. All right, and we only saw that there was one variable that affected the pendulum, and that was length. And so the length of the string divided by the gravitational field strength, or the gravitational constant G. And when we're on Earth, G equals 9.81. Whenever we're on the moon, G equals 1.6. And whenever we're on Jupiter, I think it's like 25 or 27. So this is going to be the equation to solve for the time period of a pendulum. So just a quick recap. We've had 3 equations so far, and that is that the frequency of the object equals 1 over the time period, and that the time period for a spring equals 2 pi square root of m over k. And what this says is it says that, well, on a spring, if you have a stronger spring, it's going to take less time because that number is going to go up, and so the time period is going to be less. And if I have more mass on the spring, well, then it's going to take more time. And then I also have the last equation, which is the time period for a pendulum, which equals 2 pi L over G. And just so that we can define the difference between the time period of a spring and the time period of a pendulum, let's just say that's the time period of a spring, and that's the time period of a pendulum. Okay, now you're going to have some problems to work using these, and I'll do a couple example problems for you. If you have any questions, let me know.